Got some really good feedback on the last one of these that I did. So going to spend a little time on this paper from Google DeepMind. This is from Pushmeet. So I'm now following him, VP Google DeepMind, Chief Scientist, Google Cloud. So he's introducing AI Co-Mathematician. So they've got the technical paper and the leaderboard here, Frontier Math LLM benchmark. And you can see here, this is quite a significant increase. So same amount of sort of variation, but the mean or the median is huge. We need to check which of those it is. But, you know, that's a significant jump. Pretty cool to see this stuff happening. Pass one accuracy, it doesn't say. Okay, cool, that's the accuracy, and then with some error, fair enough. Cool, so yeah, this is the paper, and I'll zoom in a little bit so we can read this more nicely, but actually, I haven't pre-read it, but there's some bits that I thought, that I had a little scan, and yeah, I think it's quite interesting. Okay, cool, so AI Co-Mathematician, accelerating mathematics with agentic AI. We introduce AI Co-Mathematician, a workbench for mathematicians to interactively leverage AI agents to pursue open-ended research. And I guess this is probably the constraint, right? Rather than it being something specifically to solve one benchmark here or there, it's a tool, a workbench. Optimized to provide holistic support for the exploratory and iterative. Yes, this is the thing of mathematical workflows. So the idea of like not iterating on things is kind of wild to me. You don't need to iterate on things that you know, but if you're doing anything like moderately interesting, it's often exploratory or iterative. You know, I'd go so far as to say it's very difficult to create value in places that are well explored, and you don't need things to be iterative. Ideation, literature search, computational exploration, theorem proving, and theory building. By providing an asynchronous stateful workplace that manages uncertainty, refines user intent, tracks failed hypotheses, and outputs native mathematical artifacts, the system mirrors human collaborative workflows. In early tests, so again, unsurprising here, but maybe one of the reasons why this is working is that it's adapting itself to existing workflows rather than trying to both change the workflow and also succeed in a sort of abstract way. In early tests, the AI Co-Mathematician help researchers solve open problems, identify new research directors, and uncover overlooked literature references. Pretty cool. Besides demonstrating a high interactive paradigm for AI-assisted mathematical discovery, the AI Co-Mathematician also achieves state-of-the-art results on hard problem-solving benchmarks, including scoring 48% on the Frontier Math Tier 4, a new high score amongst all AI systems evaluated. Will be interesting to see how this actually works, because again, looking at this, this is just kind of like model on its own versus like model and agent plus human. So, it's going to be interesting to see how they do that. You kind of like, you would hope that having a suite of agents and humans co-creating would do better than just a model on its own. It'd be interesting to see where we get to. Which parts of the system are sort of responsible for that increase. Okay, cool. Maths is multi-dimensional, complex, highly iterative, while the publication record is built almost entirely on polished, rigorous proofs. A mathematician's day-to-day work has long been understood to involve activities traditionally concealed from public view. Beneath the final formalism lies a deeply exploratory process where initial intuitions are tested, counterexamples are discovered, and core definitions of proofs are subject to continuous cycles of refutation and revision. Recent years have seen an explosion of capabilities in AI for mathematics, rapidly expanding the field across several distinct dimensions. The realm of autonomous mathematical reasoning, building on early systems like Minerva, the vast body of subsequent work, the field has now advanced to breakthroughs like the autonomous research system Alethea. In the realm of exploratory search, AlphaEvolve and systems it has expired allow researchers to uncover novel algorithms and structures through continuous steerable evolutionary runs. In the realm of formalized mathematics, alpha proof, related systems, and interactive environments, such as Aristotle, have deeply integrated reinforcement learning and language models into verified mathematics and open source proof assistants. So I'm learning lots here. I knew about AlphaEvolve, but the rest of these are sort of new to me. So yes, certainly interesting to have a look into those. Again, don't want to spend 3 hours on this, so probably not in this video. Okay, cool. Meanwhile, the inference scaling models currently powering commercial chat interfaces have already brought immense problem-solving power directly into the hands of mathematicians. Yet, first-hand experience with these systems reveal that a critical dimension of mathematical research remains undersupported: the orchestration of these capabilities into a long-term, stateful, collaborative workflow. And I don't think they mean workflow in the sort of DAG. They mean workflow in terms of like human workflow, but we'll validate that as we go. Day-to-day mathematics is rarely a sequence of isolated queries or computer-assisted proofs. It involves managing uncertainty, synthesizing disparate literature, drafting and revising intermediate artifacts, and tracking complex branching hypotheses over days or weeks. Because standard chat interfaces are inherently transient and specialized, engines lack broader context, researchers must act as the manual connective tissue between conversational brainstorming, formal provers, and computational scripts. While software developers increasingly rely on AI-powered coding environments to provide this exact kind of orchestration, these tools are fundamentally optimized for the lifecycle of code, not the unique abstractions, proofs, and artifacts of mathematics. So yeah, this is super interesting because again, it's basically like taking all of the things that we've learned in software and applying them to another different environment. So yeah, super interesting. To truly accelerate discovery, we believe the next phase of AI for mathematics must focus on this missing dimension of orchestration, natively supporting the full messy reality of mathematical activities. To understand how to build a native environment for these activities, we can look deeper into the field of software engineering. Yeah, so again, it's taking these advancements. So, one I've talked about a lot is language server protocol or linters. Grammarly being a perfect example of like a grammar linter in prose, but you could lint for almost anything now. Recent advancements. So again, obviously they're going to talk about Google Anti-Gravity, Claude Code, and OpenAI Codex have demonstrated the transformative potential of efficient, interactive collaboration between humans and agentic AI systems. One of the reasons behind the success of these systems is that the pre-existing software engineering practices embody the paradigms necessary to capture and accelerate iterative exploration. And this is really important, I think. It's, iterative and exploration. If you already know how to do something, like, you don't need iterations, you don't need to explore. But again, most of that is like boilerplate, off-the-shelf stuff can be templated. But more often than not, if you're doing some product building, you should be doing iterative exploration because you shouldn't be doing the things that don't differentiate your product. You should be using off-the-shelf pieces. Informal software specifications, such as design documents, informal, highlight there, allows agent to work autonomously for long periods of time whilst remaining on a predefined path, and continuous testing pipelines provide an automated flow for verification, while version control seamlessly tracks and maintains the evolving state of a project in a manner familiar to human professionals. In contrast, almost none of the analogous activities in the everyday work of a mathematician are routinely automated. To establish this missing agentic flow for mathematicians, we introduced the AI Co-Mathematician, a workbench for mathematicians to interactively leverage AI agents to pursue open-ended research based on the latest Gemini language models. So again, interesting that basically what we're saying here is like the innovation is a product one, is a human interface to manage some of the complexity and take care of some of the verification, some of the testing, some of the version control and the search and those sorts of things. I should probably have just read this instead. The AI Co-Mathematician provides a stateful, interactive workspace where a project coordinator agent delegates complex tasks across parallel workstreams, allowing the user to direct and interact with an evolving research process rather than waiting for end-to-end autonomous execution. As with other agentic systems, the AI Co-Mathematician is a harness designed to be used with standard commercially available language models and does not rely on any custom model behavior or training. So really useful here in terms of again, saying effectively there's no machine learning going on in the development of this AI. It's all code and prompts and maybe an agent framework and that sort of thing. Importantly, the AI Co-Mathematician is designed to complement existing frontier approaches rather than replace them. And again, there's definitely something to say about reimagining process, but changing process is way harder than accelerating existing process. And again, one of the most important things is you get the data on where you can improve the overall quality by first turning the entire flow into something that is, able for a computer to run and then track and then get metrics. So if you encode the flow, then you can start working on changing it rather than trying to reimagine it from first principles and then persuade people to use it and then show that it's better than their previous flow. It's way easier to go to where people are. By establishing this stateful architecture, we pave the way for powerful underlying engines. Some M dashes here. Interesting. Whether autonomous reasoners like AlphaProof or Lithia or evolutionary iterators like AlphaEvolve to be deployed dynamically within the human researcher's interactive loop, while the AI Co-Mathematician itself is currently slightly limited, subject to a limited initial release, our goal is to develop future products that grant much broader access to this interactive paradigm. Okay, cool. So yeah, not out yet. We can't see it. In the remainder of this paper, we detail the philosophy and architecture behind the AI Co-Mathematician. So hopefully this is going to be really useful for building analogous AI products. And yeah, they'll share the early results. Core design principles grounds these principles in practice through a concrete walkthrough, highlight the programmatic constraints, adversarial review loops that prevent the system from taking the easy path on intractable problems, and the parallel work streams which enable multifaceted research. Evaluation strategies for interactive mathematical agents and early qualitative results. Okay, cool. Generate verifiable insights. Section 6 evaluates the system performance on static problem-solving benchmarks, providing a baseline measurement of its underlying capabilities. 7 describes the challenges, limitations they encountered in developing the AI Co-Mathematician. Finally, outlining the vision for the next era of AI-assisted mathematics. So again, yeah, starting with design principles, I like this. Overriding goal of our design is to support human mathematicians in their own work. Yeah, I mean, I've said this before, technology exists to help humans. If you're not thinking to help humans, I don't know what you're doing. Like, it's very difficult to create value if you don't make humans happy. Now, you might just make one owner of a business happy, but yeah, you're probably going to get a lot more leverage and a lot more buy-in if you help more humans. As Thurston famously argued, mathematics is fundamentally a social enterprise aimed at advancing human understanding, rather than merely a machine for generating formal proofs. Yep, I like that. To genuinely accelerate mathematicians, AI tools must integrate into this human-centric reality. To this end, the AI Co-Mathematician is built to capture the enduring aspects of professional mathematical workflows, while pragmatically navigating the current strengths and weaknesses of AI reasoning. Our design is grounded in both historical accounts of mathematical practice and our experience observing and improving previous systems for mathematical discovery, especially those developed at Google. We relied on 7 core principles to guide this design. Love it. Embrace mathematics beyond proofs. Okay, cool. I like that because it's already saying the problem isn't just the problem. The problem is the environment around the problem. Genuine mathematical discovery involves a complex mixture of activities beyond theorem proving, such as iteratively refining research questions, combining the literature, brainstorming, and running extensive calculations and numerical simulations to build intuition, to name a few. Putnam argued that reducing mathematics to isolated logical formalisms ignored the deep quasi-empirical reality of the discipline, and our design deliberately reflects and supports this holistic multimodal reality rather than, I mean multimodal in terms of modes rather than models, rather than indexing solely on final theorem proving. Support iterative refinement of the intent. Again, no one-shot, put in, solve Fermat's last theorem, outcomes, perfect answer, nonsense. In many domains users know precisely what they want from the outset. I'm not certain that is actually true. I think actually in almost every domain, people don't really know exactly what they want, and a lot of the work and the problem is not of taking a perfect, turning something that is precisely defined into something else is relatively trivial. Actually, the problem is normally, again, this heavily dependent on continuous iteration and refinement. People don't really know what they want, and so, yeah, you have to have this continuous iteration and refinement. As Polya demonstrated in the work on plausible inference, formulating the right question often requires extensive heuristic guesswork just to get started. As argued by Georg Cantor in Mathematics, the art of proposing a question must be held of higher value than solving it. And I think this is true for many other areas as well. Good questions are often much more useful than good answers. Once you have the right question, sometimes the answer's very easy, but getting to the right question is really challenging. Experience with systems like AlphaEvolve corroborates this. Mathematicians spend considerable effort actively iterating on exactly what the problem to focus on. Test again, M dashes, so for sure used some AI to generate this. Testing with smaller runs on related problems before scaling up. We designed a flexible interface that supports multiple exploration paths, so users can fluidly refine definitions, questions, and conjectures. This is great as well because, again, if you've got some sort of poorly formed ideas, but you've got many of them, you can parallelize that, and I think that's quite interesting to sort of, just like, not have an intuition in a particular area and then, send out multiple feelers and, invest in those that bear fruit, and discard those that don't. Produce native mathematical artifacts. Research mathematicians have standardized ways of working rather than outputting transient chat logs or prematurely polished manuscripts. Perfect sentence. The AI Co-Mathematician centers its processing around a living working paper. In a traditional workflow, drafting and commenting help a mathematician build a rigorous mental model of the project, knowing exactly which parts are solid and which require further attention. Because autonomous reasoning systems can perform much of this exploratory work asynchronously out of view, the user risks losing this organic context. To help the user reconstruct their mental model, our system tracks the evolving state of the research and visualizes it through inline text and margin notes. I like this. I really want to see this UI because I think there's going to be some interesting things here around like that approach, and especially can see that being something that could be used in any kind of text editing workflow, of which there are many. By explicitly providing context, such as the provenance of specifying claims or the contentiousness of a drafted lemma, the system surfaces the AI's underlying process in a format completely native to the mathematical community. So again, I guess this kind of looks like getting feedback on your existing, your sort of draft paper from colleagues, right? And collaboratively working on things and then pointing in the direction of different pieces of research. And so, yeah, this makes a lot of sense. And again, this is awesome in terms of like, for me, a lot of this stuff is like getting that insight, getting that research, getting that, feedback is an insanely useful way of using AI. And highlighting things that you hadn't thought of, even if you then reject them. It gives you a more well-rounded view of how things could be. Enable asynchronous interaction and flexible steering. Rarely linear. To mirror this, the system. So again, very few processes are truly linear, and so this is why I get frustrated when you see a lot of like workflow, like hard graph workflows. In AI agents, actually you want a lot more flexibility often, unless it's a more simple thing, and then you probably can get all the way to determinism potentially at some point. To mirror this, the system operates not as a single conversational chatbot, but as an asynchronous team. Under the hood, a messaging system allows multiple specialized agents to work in parallel. So they're probably using A2A, because it's Google. Because these agents run async, the system can allocate substantial computational to a problem without blocking the user, allowing heavy compute and continuous interactivity to coexist. Yeah, just makes sense not to block when you're doing work in the background. Rather than being locked out while the system thinks, the user can communicate directly with the central project coordinator at any time to intervene, bypass current constraints, and steer the ongoing research. This collaboration is also bidirectional. If the agent stalled, the project coordinator agent transparently flags the roadblock and requests human assistance to help unblock the system. Manage cognitive load via progressive disclosure. Amazing. This is one thing. So complex research, again, just dumping all this research for the human is, you can, an AI or a machine can process so much more text than a human can. It's crazy. So you need this progressive disclosure to sort of be able to double click and go down, explore multiple parallel avenues, backtrack from dead ends, and reuse intermediate results. So yeah. A long unstructured chat quickly becomes unusable if high-level strategy, i.e. try fixed point approach, is mixed with low-level execution logs of multiple background agents. To control how much information is revealed to the mathematician, our collaborative interface employs progressive disclosure, separating high-level intent from low-level execution by mirroring the agent hierarchy itself. By default, the user interacts primarily with the project coordinator agent. So to some degree, this is like a kind of gas town for mathematicians. So yeah, could be quite interesting. And they've got specialized sandboxes. However, the system offers drill down. Okay, yeah. And this is important as well. You want to be able to go in and check the working of any particular thing. Track, manage, and communicate uncertainty. High standards of rigor, where a single flawed lemma or hallucinated reference can undermine the entire paper because of the reasoning capabilities of base models. Are prone to unpredictable shortcomings. Their zero-shot outputs produce a baseline of uncertainty into a domain that demands precision. Rather than hiding this friction, the system's architecture is designed around the life cycle of this uncertainty. It tracks uncertainty by maintaining a detailed version history, used primarily by the agent, but also available to the users, to monitor how claims evolve or called into question. It manages uncertainty by training compute for validation, through continuous reviews, numerical simulations, and systematic citation checking. And it communicates friction by recognizing when the reviewing process stalls on specific parts of the argument. By using the inline highlighting and margin notes to draw the user attention to these stalled sections, the system highlights areas of the working paper that warrant closer human scrutiny. By treating uncertainty as a core variable to be orchestrated rather than a simple error state, robust mathematical output can be synthesized from inherently unpredictable models. Preserve the history of failed explorations. Yeah, perfect. I mean, one of the problems with research just in general is that only positive research is published. And so, yeah, like, knowing what does not work is often as important as knowing what does work, because otherwise you just spin your wheels going down paths that don't work. And anyone who's used AI knows that it will continually rehash some of this stuff. While they're configured to navigate around, rather than silently restarting or scrubbing the history, the architecture treats dead ends as first-class permanent outcomes. Preserving this negative space of the project's history is crucial for tackling difficult mathematical problems. By maintaining a durable record and exhaustive strategies, failed goals and exhaustive strategies, the system provides context for the user and the AI to collaboratively formulate new, more informed work streams off the back of those failures, reflecting the view that refutations are fundamental to mathematical progress. Okay, cool. Let's have a walkthrough. In this scenario, there's an open problem in computational geometry, proving the outer bounds of an area of a sofa that can move around both left and right-handed angle corners. It's like the Friends problem. And with lower bound explored in recent work on applying alpha evolve. Okay, cool. Can you tell me the current state of your investigation? Yeah, right, like latest draft report outlining that. Have you been able to make any progress in implementing a Python library and different workstream coordinators, different specialized sub-agents? Okay, cool. So, yeah. Doesn't give us much. This is very high level. Okay. Arrows denote standard communication pathways which are utilized to collect information for and distribute instructions from the user. Okay. Also interesting to see how these agents interact, because I think one of the things is I always think when you go sub-agents and orchestrators, you end up with all the problems of distributed compute, and so it ends up being quite annoying to sort of have that multi-threaded approach on different parts of the thing. It's incredibly useful for the speed up, but you then have if I'm referring to line 40 and I delete a lemma, then that's the thing is no longer on line 40, right? And you've got to match all of that stuff. It's not too hard, right? We've done it with loads of other things. Okay, cool. So the user discusses with the top level project coordinator agent, and all of these are delegated. Okay, cool. Initial exploration, standard zero-shot LLM requires the unit to front load a perfect prompt, reflecting our principle to support the iterative refinement of the intent. AI Co-Mathematician begins with an interactive onboarding phase designed to help the user formalize their intent. Nice. So again, this is a curated product experience that is domain specific and helps sort of flesh out and gather more information and basically let's see. I'd like to set up a project, see if we can prove some upper bounds on the variance of the moving sofa problem discussed in this paper. Top-level project coordinator agent does not immediately start working on a solution. Instead, opens a dialogue that acts as a sounding board. From the text, Bake has already proved that Gerver's lower bound is sharp for the classic sofa problem. However, the upper bounds of the other two variants are still open. Would you like to focus on one in particular, or are you aiming to prove that specific lower bound is sharp, or simply establish any new rigorous upper bound? Once the user clarifies, they formalise the understanding of the project central question, high-level goals, and presents this to the user. After reading these proposals in detail, the user requests changes to the wording of the goals, and the project coordinator updates them. So, I guess one thing is is there any ability to actually edit the text here? For me, I find that editing text by chatting with an agent is not always my favourite method of interaction, in that if I want to make a small change, it's way easier for me to just make that change than for me to tell an agent to make that change, and you have no risk of any other parts of that text changing, because a lot of the time, rather than doing inline edits, agents will naively rewrite out the whole thing, and so you sometimes miss other bits and pieces from those edits. Okay, cool. Formally approves the goals, allowing the project coordinator to move on to the next phase of the project. So I like this stuff because when you've got these formal approvals, that's an opportunity as well to have some sort of, confirmation of which tools and where are going to be used, which can be great for governance. So, for example, you might have a budget of compute that you want to spend on this, and this formalization would be a perfect time to set some of those boundaries, those non-functional requirements, and have them agreed on by the user and have some sort of mandate. By treating the interaction as a dialogue, the system ensures downstream resources are directed towards the actual refined intent. Okay, cool. Research question and goals. Nice. I like this stuff. It looks really nice. It doesn't look very much like a paper, but it looks a lot more like a product launch. Anyway, branching the research with the goal to find the system manages the cognitive load via progressive disclosure. The project coordinator delegates work to parallel work streams, each associated with one of the pre-approved goals. So yeah, okay, cool. One work stream per goal, managed by its own work stream coordinator. Interesting, choice, right? Because literature, computational framework, execute the search. So yeah, there's already a problem in terms of making sure that these are actually independent goals. If they aren't independent truly, then you're going to have coordination across the streams. So interesting to see if they talk about that. Along with any specific instructions which the project coordinator chooses to provide. Each coordinator performs a linear sequence of actions which may include delegating to specialized subagents. The diverse nature of these work streams highlights the system's capacity to embrace mathematics beyond proof. Currently, our specialized subagents are based on standard LLM calls, including Gemini DeepThink, and do not make use of advanced research systems such as AlphaInvolve, AlphaProof, or Alethea, but we illustrate the points in this process where they would naturally add value. So that's really interesting in terms of they've achieved this benchmark without using those tools. So, okay, cool. Scenario where the project coordinator starts one work stream. It's possible to have multiple work streams defined per goal, or for goals to remain unpopulated with work streams until work they depend on has been completed. Okay, cool. So there is a bit there around that. Goal 1, literature review. Okay, cool. Like computationally extensive search tool discovers key papers containing the machinery used for previous upper bounds in the SOFA problem. With pointers to important references, it queries them directly using specific web and literature access tools to identify the exact statements and proofs of key work. So this is, like a really good deep research approach. Computational framework, designing the required computational framework based on the strategies. I'm wondering if they use like Lean, which is quite interesting. Nope. Based on high-level strategies, using sub-agent creation tool to dispatch Gemini DeepThink to prove that this could give a rigorous upper bound as required. Once it is proven, it uses another sub-agent creation tool to create a coding agent, instructing it to implement the required Python library with associated test and demonstration cases. Each of these agents gives... so I'm wondering what Python library they're using, because there's a couple that could be interesting here. But yeah, again, like I think to some degree you're constrained by your tools, right? And if that library does something well, then it might be great for that, but not for other bits and pieces. Yeah, so again, another figure. Cool. Updates user-facing workstream, reports with details of the proofs, and provides links to key code files. Perfect. All proofs in the existing system are purely informal. Okay, so yeah, no formal methods yet, like Lean or TLA. Not that TLA I think is useful for like pure mathematics. Built the possibility of adding a formal prover such as alpha proof would allow for increased confidence in the correctness of proofs for those that are able to be stated and proved with existing formal mathematical libraries. Alternatively, using a stronger informal proving system such as Alethea would add considerable power to the system at an associated compute cost. And goal 3, search, find a branch and bound search. Okay, the shared file system to import the library developed in the previous workstream now uses parallel code execution tool to scale up the search beyond a single script. So it's basically fuzz testing the new theorem, right? Parallel code execution requests are run on separate cloud machines. The results of the search are collated in a single file. Okay, yeah. So just like go through and again, a lot of the time when you've got formal provers, you end up with a similar sort of thing, right? Where you've got a model checker that goes through and explores in a sort of breadth or depth first search all of the possible situations and see if it holds for them. So it's the same idea here. In software, we'd have fuzzing or property testing in the same sort of way. In the current prototype, such computational searches are executed as a combination of standard agent primitives, but with the addition of evolutionary search, such as AlphaEvolve, would provide a supercharged engine for such optimizations. Yeah, so this is a more complicated search, but yeah, effectively search. Right, there you go. They've made it look nice and linear. Okay, this is what a single work stream, so I suppose it is linear. Okay, interactive steering and hard constraints. So maybe they are going to talk about some of the things I talked about at the beginning. Once solved difficult research standard, find invalid shortcuts, hallucinate lemmas, handwave details, and claim success prematurely. One of the defining technical features of the AI Co-Mathematician is the application of hard programmatic constraints to prevent these failure modes, combined with active human steering by the user. So yes, I think key here is something I've been banging on about, is like, you can put in actual guardrails, not guidance. Guidance is really important, steering and guidance, but like you can put in hard constraints that stop bad things from happening or make it much more likely for the right thing to happen as well. or even the right thing has to happen or it fails, which is also a good behavior, right? Because now you know there's a point at which it fails. Okay, during the computational exploration, if the search space explodes, the naive backtracking approach initially proposed may fail. In this situation, a coding subagent is bound by strict rules. It cannot mark code as finished until all the tests pass and a reviewer agent accepts the validity of the code and golden values in the tests. Okay, cool. So again, sounds like they're doing a bit of TDD, which is nice. Because the reviewer agent repeatedly rejects the failing code, the workstream coordinator agent is blocked. Rather than silently restarting, the system preserves this failed exploration. So they talked about this being first class, which is great. Forced to manage and disclose its uncertainty, the project coordinator agent surfaces an alert to the user. Our initial implementation of the search is not efficient enough to find the result we need. There aren't any other examples in the literature. Do you have a mathematical institution for finding a better pruning strategy we can apply? Okay, cool. Crucially, the user is not locked out while the agents work. Via the chat interface, the user reads the project coordinator's update, actively steers the project, sending a message to suggest a topological pruning heuristic, and directing the coordinator to create additional work streams to investigate new bounding strategies while current work is ongoing. Okay, so this is very cool and yeah, makes perfect sense. After the user steers the system past the computational bottleneck, the work streams conclude their specific goals. However, the final output is not a transient chat message. Each workstream coordinator agent is responsible for producing as its main output a compiled and reviewed LaTeX write-up, which is displayed prominently to the user when they open the workstream. Okay, cool. So they must meet specific criteria. And this is great because this is probably, a summary of their evaluations. Exposition. The draft must exclude an explanation of the research process that led to the outcome, not just the final result. So show you working. The document utilizes margin notes to provide additional information. So again, okay, cool. Note might read, pruning heuristic. This is really nice though, because it kind of shows your progressive disclosure in a way that's really normal to us. Internal linking. As well as external literature, references made to internal documents created by the agents, giving the user direct entry points to audit a shared file system. Nice. Before a report can be marked as finalized and the workstream completed, the report must be submitted to a paper review process where it's scrutinized for content and style. Okay, very good. Eval in the flow. All of whom have tools and capabilities to cross-check references and code outputs, as well as logical correctness. Reviewer agents persist between review rounds, creating an iterative process. Okay, cool, which only concludes once all reviewers have formally improved the report. Nice. To avoid infinite loops, if the workstream coordinator agent is unable to pass the review process, it can escalate this issue to the project coordinator. Makes sense. Unfinished, yeah, escalation message, and the user can take a look at the report or unblock in some way. Nice. This is going to be really interesting, I think, the evaluation of interactive mathematical agents. Historically, progress has been measured against static problem-solving benchmarks. Today, the field relies heavily on the benchmarks. Okay, cool. Links to all of them there. Okay. However, with frontier systems now demonstrably performing at or above the level of experts at raw problem-solving ability, we believe the incremental value of improving this ability is reducing, and that progress in AI-assisted mathematics is now at least partially bottlenecked on other capabilities that reflect the broader workflows of professional mathematicians. Yeah, this makes sense. Yeah, the bottleneck moves, right? Once you get to a certain level, you don't need to solve a problem to make it not the bottleneck as much anymore. And yeah, we've seen that in coding, whereas writing code is not necessarily the bottleneck anymore, but it's very quickly moved to verifying code and making sure that it actually provides value and that you're writing the right thing. This implies, firstly, that AI systems should be measured against a wider array of tasks. Deep search QA for general purpose fact finding, and hard to verify for mistake finding and competition. Oh, okay, that's very cool. Mistake finding and competition mathematics proofs. Measure capabilities with exact analogues in mathematical research process. But to our knowledge, no similar benchmarks have been developed for the setting of professional research mathematics. Clear measurement of these auxiliary capabilities and improvements against them will become increasingly important. Okay, to reduce the severity of the jagged frontier, which is that, some bits do well and some bits do terrible. And the associated impedance mismatch between human driven and AI-driven mathematics. Yet more importantly, so again, they're calling for a new benchmark, which makes sense to me. AI for mathematics systems should be considered as human in the loop by default, and the advancements and achievements measured accordingly. This echoes our design principle that the foremost purpose of our system is to assist mathematicians with their work, not to achieve success independently of them. And this makes so much sense. Like, to me, yeah, I think, again, it might change the workflow of mathematicians, but it is very unlikely to replace mathematicians. So, like, again, every 9 is maybe 100 times more effort. So to do 90% of the work, 99% of the work, 99.9% of the work, 99.9999% of the work, you get speed ups, but like, yeah, for me, it kind of approaches infinity rather than, at some point, you've got to have someone who wants to prove something, right? With this framing in mind, we first present the results which have arisen from mathematicians directly using the AI Co-Mathematician. Section 5, followed by measurements of the AI Co-Mathematician's static problem-solving performance. Okay, cool. So early with mathematicians. Okay, small number of professional to use in their own research. Wide range of use cases reflects its broad applicability and integration into standard research workflows. So that's good. It's not just specific problems, it's generally their workflow. Functional aid, navigating disparate literatures, performing numerical experimentation, obtaining proofs across several domains. Okay. Notices. Whilst many users have successful interactions with the AI community leading to novel discoveries, there's been a range of feedback and satisfaction with the tool, and other users have found it less effective for their work. Okay, yeah, cool. You're not going to please everyone, right? That's never the goal. It should never be the goal, because you'll never do it. We discussed some of the challenges. Okay, cool. Notably, all results showcased here were produced independently by mathematicians using the tool directly, without any supervision or intervention from Google DeepMind researchers. Korovka problem. M. Lackenby used AI to investigate several problems in topology and group theory. Okay, cool. And it resolved an open question. Lackenby's process in this case illustrates the value of mathematician in the loop style of interaction. Simply try typing in the problem statement. The first result to come back was a proof that the system itself marked as incorrect. A workstream had written it up without an argument, but then a reviewer agent has found a flaw. However, when looking at the paper, Lackenby realized that despite this gap, it contained what he called a really, really clever proof strategy. Okay. Furthermore, when he read the reviewer's critique of the proof, he realized, hang on a second, I know how to fill that gap. He pointed out a way to correct the argument, and the system was able to write up complete and correct proof. Nice. Okay, downloaded the document, applied his own revisions, generalizing the result and adding examples before uploading it again and asking the project coordinator to create a workstream for a final review. It did so, spotting 2 minor issues in the paper that he fixed for the final copy. Lesson from this case is the back and forth between AI and mathematician was crucial to the resolution of the problem. To Lackenby, this suggests the system works best when the user is familiar with the area. And we've seen this over and over again. Experts get better results. It's always worth becoming an expert because you get more from the AI. While one might see this as a limitation, he adds, what's the point in getting it to solve a problem that I have no idea about? Great point, There's no way of verifying. If you're not an expert mathematician, and I'm certainly not, you're never going to be able to work out whether it's actually correct or not, whereas Lackenby is and was able to do so. Create a coding subagent, computational search for just non-just finite presentations. Presentations. Analyze these and performs literature searches, relevant theory. Noted that this did not negatively resolve the conjecture, as groups may have multiple presentations, and finding one not just finite presentation does not imply that none of them are just finite. But decide to conclude its workstream here with sharp conjecture based on this argument and send forth. Yeah, so this is also intelligent because although it doesn't disprove the theory, you can use it as feedback before investing in more computationally intensive checking. Back and forth. Reviewer spotted a method that could be used to prove the conjecture in the positive direction. Agreed with the reviewer, pivoted the workstream, led to the draft. Okay. Sterling, another early user. Sterling coefficients for symmetric power representations, specifically conjectures hypothesized in certain binomial expansion. Coefficients are not only strictly positive, but also form a log concave sequence. Brief note, background of the conjectures, known methods. Primer also included suggested directions derived from prior experiments with other systems, such as Alpha Evolve. It had hinted at a possible direction to recover an inductive formula for the coefficients. Structured posing of questions was one he found effective with other AI systems. The AI Co-Mathematician established proofs, currently in detailed human review, for 2 of the conjectures in separate workstreams. It additionally provided detailed computational evidence for its claims as well for investigations into the unproven conjectures. Noted the design of the system helps in various ways. Not only was it easy to follow the green ticks checking off tasks, but more importantly, a marginal comment in the finished document alerted him to a key insight, which he was able to ask about in the chat interface. It's not trivial how to use this now, and it will make a big difference between mathematicians and how they use these models. So it's still not perfect. Coding subagent, observed conjecture, Gemini DeepThink to propose new proof strategy. Okay, cool. A lemma in Hamiltonian systems. Okay, cool. Sorry, Rezchikov, I think I'm going to skip over this one, but it's two. One was about exploration of an approach which did not seem to work. It added the value was the system let him reach a dead end faster than otherwise. This is really important. I can imagine it being incredibly frustrating to work for weeks or months on a dead end. If you can find it very quickly, that's actually a real time saver. Something that's almost impossible to measure, but you feel that like relief of not having to go down that path. I could easily have spent a week dreaming about what was there. Instead, I just moved on. Qualitatively, of the correct proofs seemed comparatively high. I'd rank aesthetically its general style of proofs as the best of any model I've got to use. That's nice. Literature review, follow up with literature, and produce the proof. Cool. So designed to communicate via long-form reports. We developed a custom mode where the system is not able to receive external input beyond that of the initial question and returns a single final answer. So they then tried to make it a black box. So hard coding the project goal to solve the problem. Cool. And this is their internal evaluation performance. So with Gemini on its own, DeepThink on its own, with Gemini and DeepThink. So yeah, nice. Fixed time limit after which the required to give a final answer, 24 hours. Wow, 48 hours for frontier math. Most problems finish well within the time limit. For hard problems without human intervention, the system occasionally continues beyond this, especially in cases. So that's wild to be running it for that length of time in my mind. Again, this is a bit of a hypothetical because it sounds like it's supposed to actually highlight this and co-create with the user. Okay, so while there's not an issue with the inference limits, I actually want it to be used by people, so it has to be like, so it says a broadly comparable number of models and tool calls to long AI-assisted software engineering session. 100 unleaked research-level mathematics problems with code, checkable answers, sourced from professional mathematicians. Nice. Significantly outperforms a single call to Gemini. Unsurprising, a single call to the DeepSync. Cool. We see that the AI Co-Mathematicians reduce the core question to Boolean satisfiability SAT problem, which it solves using the PySat library. Oh, nice. So yeah, we've got one of the libraries that we used. Interesting. I've not used PySat. I will come back to that later. or probably not, because we're already at almost an hour. Several non-trivial adaptations were required to make this framing work. Okay. For a natural comparison of the external frontier benchmark conducted blind. AI Co-Mathematician achieved a new high score, correctly solving 23 out of 48. Once the two public sample problems excluded, an accuracy of 48%. Okay, cool. So it correctly solved the two public sample problems. The problems solved correctly included 3 problems which had not been solved by any previously evaluated system. Though it failed to solve 2 problems which had previously been solved by at least one system. So again, maybe shows a little bit that there's like there's some bias in there that leads it down some tracks. This isn't a sort of universal better way. There's different ways of thinking maybe within this that kind of lend themselves slightly more to different problems. Or there was some error in the process that another model was able to do. Okay, so they're normally a standard agentic harness developed by Epoch AI. This offers access to Python interpreter, but also places a hard limit on the number of tokens used in the agent trajectory. In our setup, we only use our own tool. Okay, no limit on the number of model calls or tokens generated. This means our system likely has a higher inference cost than previous system. And if I'm honest, probably makes the benchmark result much less valuable, right? Because if, for example, it uses 10 times as much inference and all of the other models are constrained to use that volume of inference, then, it's not really comparing apples to apples, is it? Cool. Reviewer pleasing bias, false consensus. Yeah, this makes a lot of sense. And again, this is probably stuff that should be that is in their evaluations. Okay. Yeah, okay, cool. So when there are errors that can no longer be detected, such arguments can also be tricky for humans to tease apart, which has been highlighted as a limitation. Yep. Similar pathologies in prover-verified dynamics have been noted in the literature. Though this behavior is relatively rare, it represents a violation of our core principle of explicitly acknowledging uncertainty. Intractable disagreements, non-termination. Okay, cool. It can fail to terminate entirely. So, yeah, it can go into a death spiral. Makes sense. System autonomy requires seeding control. Significant risk the model encounters unplanned for, which is amplified many hours without requiring immediate human input. Current model's judgment on what to do in such a case is far behind human capabilities and expectations. Yeah, makes sense. I think that stuff's coming. But again, it's probably domain by domain, right? Semantic meaning of representation. Mathematicians tend to associate a well-typeset document with a corresponding level of rigor in the content, an intuition that is belied by LLMs, which excel at generating flawless LaTeX formatting while frequently struggling with rigorous logical verification. We see this all the time. Things that look good, look plausible, but the content isn't quite there. So, yeah. Like we attempt to reduce this by highlighting. So again, actually they're like kind of on purpose making the output look less polished to nudge the human into it to be more skeptical, which I think makes a lot of sense and something to think about when you're building these products. Maintaining signal to noise in the literature. Okay, cool. Yeah, so again, they can write their own papers now, and then you've got a bunch of AI papers and the peer review system. Yeah. Okay, cool. Recently passed multiple technical milestones, human level and superhuman performance across a variety of mathematical benchmarks. want to genuinely accelerate scientific discovery. Solving static, well-defined problems is only part of the solution. The frontier of mathematics research is not linear conversation or a series of disconnected puzzles. It's a messy, overlapping, highly iterative process defined by unproven intuition, branching hypotheses, and complex human collaboration. Yeah. Okay, cool. I thought that was super interesting. I think there's a couple of takeaways for me that are effectively like, if you design for humans, you are much more likely to get your system to be used. You are much more likely to win adoption, and that will allow you to get more data on the process that you're going through. I really like their idea of that working document. It sounds like this is basically an IDE for mathematicians, which makes a lot of sense. I was wondering whether they were going to do some like lean stuff, right, where they've got like this kind of bits and pieces, which is kind of like, yeah, I was looking at some videos on it. It's pretty wild, but they've used it to prove CEDA. So AWS uses Lean to prove that their CEDA policy language is correct. Pretty cool. Yeah. So really interesting paper. Definitely read a little bit more like a product launch. But yeah, I think it's quite interesting, this. And again, like, really highlights that to get good advancements, I think that co-mathematician makes a lot of sense to me. So, can you get faster at highlighting errors? Can you, what bits can you offload and what bits do you need to highlight? The progressive disclosure, again, like not just a wall of text, etc. And then building in many layers of verification from different angles that, basically like hammer on the paper more and more. I thought this was super interesting. Hopefully you guys did too. And I probably won't do another paper for a bit, but I just thought this was quite interesting, so I wanted to jump into it.